Hey everyone, my name is Yuxuan Zhou, and I'm a third-year PhD student at University Mannheim, Germany. I am under the supervision of Professor Kuiper, and this work is done during the internship at Damo Academy, Alibaba Group, China. Our work is called SPVIT Learning 2D Spatial Priors for Vision Transformers. Before going into the technical details of our work, I'd like to introduce the background of our work. So recently, transformers have shown great potential image classification and already established state-of-the-art results on ImageNet benchmark. However, most of the remarkable results rely on large-scale dataset pre-training such as ImageNet 21K. So if compared to CNNs in a fair way, for example, if the transformers are also only trained on ImageNet 1K without any pre-training, their performance actually is still inferior to CNNs. And transformers converge slowly and are prone to overfitting in no data regimes due to the lack of spatial inductive biases. We argue that such spatial inductive biases can be especially beneficial since the 2D structure of an image is not well preserved in transformers because of the pairwise attention mechanism. And for images, the 2D structure of an image retains a lot of important information and is an important clue for image recognition, of course. So as can be seen in the bottom left corner of our poster, in that figure, we visualize our learned spatial priors. In comparing to the ones above, which are handcrafted convolution and inductive biases, which are already incorporated into transformers by previous works, such as the shifted local self-attention, which is proposed by the seminal work Swing Transformer. And comparing to them, we can see that obviously our learned spatial priors not only restrict themselves in local regions, but also remote ones. For example, the head 2 and head K, that they actually have learned to focus on the non-local regions only. And consequently, if all of the heads they work together, they are actually complementary to each other. At the same time, they are global, but each of them specializes themselves in one of the specific spatial relations. And we will show later experimentally that this kind of mechanism helps a lot with the final performance, and this proves to be effective. So to summarize, our learned spatial priors focus on different spatial relations, including local and non-local ones. And interestingly, I want to point out that at head 2, the cross-shaped window is actually resembles the one which is proposed recently in CS-Swing Transformer, which proves to beat the shifted local window design by Swing Transformer. And our work has this cross-shaped window automatically by learning, but they have handcrafted it. So now the question is, how do we incorporate this spatial priors efficiently into the self-attention without introducing too much overheads or too many parameters? We can look at the formulation of our PVIT, which is actually not very complicated. We let this omega represent our spatial prior, which, given that this one is already there, no matter learned or not. So the analogous to these attention scores, omega ij means how much weight should the ith query attach to the jth key, like as a prior. This is the difference to the EIJ, which is data dependent, but this omega ij is prior information which is static after learning. So they interact with each other multiplicatively and decide together the final tension. And to make such learning of this spatial prior automatically, we suggest to parameterize them using neural networks, and we have experimentally tried that this two-layer MLP, which is very simple and lightweight architecture, is sufficient already for this mapping, for parameterizing this mapping. And the figure below illustrates the same content as the equations, and so we don't go into the details. In summary, we have proposed a family of inductive biases for varieties that focus on different types of spatial relations, including local and non-local ones, called SPE. And in addition, we parameterize them with neural networks, and therefore the SPEs are automatically learned during training and also incorporated into the vanilla SA smartly, and we call it like SPSA. Let's look at the experiment results of our model. We can see that in the upper right figure, which is the comparison of classification accuracy on ImageNet 1K, I would like to point out that all of these results are reported using models which are only trained on ImageNet 1K, so without any pre-training, and on the resolution of 224 times 224, which is the standard resolution. Many of the works, they report very high scores either by pre-training or on a very large resolution, which is indeed not fair. And we can see that ranging from the small ones to the large ones, our model consistently beat the previous state of the art. And for example, the LVYT, which is our baseline model, and we improve over the baselines at all sizes, and also we beat the famous swing transformer, and also the very large model CAT. And our best model, if fine-tuned on the high resolution 384 resolution, we reach actually 86.3 accuracy. And moreover, we have compared our model with the baseline, which is LVYT, on the semantics segmentation task on ADE20K. We can see that including the IOU or the pixel accuracy, our model have improved on all of these metrics. So I also would like to mention that the one of the contribution by this LVYT, like the token labeling, also helps with our work a lot. We should admit that, because this is a really effective technique. But our SPSA are already based on this very high performing baseline, further improves them. And we can also see, at last, I'd like to show the ablation on the first 100 classes for ImageNet 1K. I like to show that this design, initially what I have mentioned, that the complementary focus of different heads, which is proved to be very effective. comparing to the shared SP, which means the whole network, all of the heads and layers, they share the single SP, and comparing to the unique SPs per layer and head, which is the our adopted implementation, our adopted design. It improves over that by 1 absolute percentage. And our models and code will be publicly available at this GitHub repository, and I will upload it in a few weeks. And thank you for attending this presentation. And if you have any questions, or if you would like to discuss the topic further with me, feel free to write me emails, and I'm looking forward to the discussions with you. Thanks. Bye.